I'll be discussing the improvement of populations through mass selection. The organism I chose is spiders, and I'll be selecting the top 10% of the population to breed for more legs. This will allow the spare legs to be released when the spider is caught by a predator. Our original population is a data pool of 8 spiders, a broad sense heritability of 0.85, and a realized heritability of 0.67. This chart describes the variables and equations used to make calculations and predictions. The selection intensity and standardized selection point will be used in the calculations. These values are derived from the chart at the bottom, and since we are taking the top 10%, our proportion selected is 0.1, and we will use the corresponding values. The mean of the original population is calculated by adding the amount of legs each spider has and dividing by the total number of individuals, so this comes out to 8. The standard deviation is found by adding the squared differences of the population and the population average, then dividing by the total number of individuals, which is 0.5. The mean of the selected parents is found by multiplying the selection intensity from the chart by the standard deviation, then adding the average of the original population, which comes to 8.88. The selection differential is equal to the difference of the mean of the selected parents and the population average, which is 0.88. The truncation point is found by adding the mean of the original population to the product of the standardized selection point and standard deviation. This equals 8.64. The response from selection is calculated by multiplying the realized heritability by the selection differential, which comes out to be 1.55. And the mean of the offspring is found by adding the original population average to the response from selection, which comes out to be 9.55. Here's a histogram summarizing our findings. As you can see, the mean of the offspring is moving towards the selected mean and away from the original mean, meaning the trait for more legs is being passed down. I repeated the calculations for the offspring population. The difference is that our new mean of the F1 generation is 9.55 and the standard deviation is 0.11. The mean of the selected parents is 9.47, the selection differential is 0.45, the truncation point is 9.69, the response from selection is 0.31, and the mean of the offspring is 9.86. Here's another histogram to summarize the results, and as you can see, the mean offspring of this group will have 9.86 legs, which is greater than the offspring of the parental group. A difference to note between these two graphs is that the response to selection has decreased in this one. So let's talk about why this has happened. The response to selection is defined as the extent to which a characteristic changes over time and can be used to predict heritability. If this mass selection was repeated indefinitely, the response would decrease in later rounds of selection. One reason this may happen is because the extreme type might not be healthy. Breeding spiders for more legs may not be to their environmental advantage and could cause them to die prematurely before passing on the trait. Another possible reason for this is that two traits are negatively correlated. In this example, that could mean that the trait for more legs could be negatively correlated to the ability to spin a web. Without spinning the web, the spider will not make the trap to catch its prey.